My topic is Krylov subspace iterative methods. And in the mid-20th century, scientific computing began to be widely used in engineering, physics, chemistry, and other fields. Many complex practical problems such as fluid dynamics, structure mechanics, heat conduction needed to be mathematically modeled and eventually transformed into solving large-scale linear equation AX equals to B, where A is a matrix representing the relationships in the physical system and may be very sparse or have very high dimensions. And B is an external input, such as laws or boundary condition. However, solving this large-scale problem is extremely challenging. So in the early days, uh, direct methods such as Gaussian elimination were widely used to solve linear equations. Although this method can solve the problem accurately, but it still have difficulties such as high computational complexity when dealing with large-scaled sparse matrices and large storage requirements. So to overcome the shortcomings of the direct message, people turn to iterative methods. These methods gradually approximate the true solution and only need to perform simple operations such as matrix vector multiplication in each iteration. However, the convergence speed of traditional iterative methods for ill-conditioned matrices or non-diagonally dominant matrices is very slow, which is difficult to meet the practical needs. So in the 1950s, concept of Krylov subspace occurred, which laid a theoretical foundation for iterative solutions of linear systems. And the Krylov subspace is defined as Km, where M represents the number of elements in the subspace, and M minus 1, which is right here, is the highest order of A in the subspace. And the span represents a space that is the elements in the space can be linearly combined. And the subspace has such a property that in the subspace from 1 to M, the previous space must be contained in the subsequent space. So to find the solution of the linear system, which shows here is X, and we hope to express X through the linear combination of vectors with the iteration of the Krylov subspace. This requires that the Krylov subspace composed of A and X can be replaced by a vector that we already know, so that the X can be determined. And to prove that this method is feasible, we first consider the Cayley-Hamilton theorem. This theorem states that any matrix characteristic polynomial with eigenvalue lambda, which we said here is P lambda, which is replaced by the matrix A, will satisfy that the PA always equals to 0. And we use this theorem, we get the QA, which is the same way, to equals to 0. And then we multiply both sides of the equation by x by combining the matrix A and the unknown x. And we can replace AX with the B vector and get the following equation right here. And then we put the x on the left side of the equation and we get the following equation, which is right here, where we notice B, AB, and the theorem of parameters such as a power m minus 2b and a power m minus 1b. So we find that the x can be expressed as a linear combination from b to a power n minus 1b. So according to the definition of Krylov subspace, this vector just satisfy the Krylov subspace of A and B. And so finally, we find that the unknown X can be represented by the linear combination of matrix A and vector B. And to find X, we assume that X is composed of AB and a coefficient Z. Then we can express X as follows: X equals to Z0B plus Z1AB plus dot plus Z and minus 1A power and minus 1B. And we extracted the vectors in the Krylov subspace and combine them into a matrix K. And then X can be written as KZ. And then we have AKZ equals to B. And by this method, we can reduce the dimensionality of the large matrix A. And then each time we iterate the subspace, we need to calculate the current residual. That is the difference between the current X and the real X. We calculate the norm 2 of B minus AX, which is B minus AKZ, each iteration. And finally, when the value of the norm is the smallest one, it means that the current X is closest to the real solution. So to test how this method works, I will use a MATLAB code to design a case. And first, based on the pseudocode, we need to input the matrix A and the vector B and the maximum number of iteration M. And then the code will output all the residues. And if the code is correct, and we will see that the residues will gradually converge to 0, which means that the X is close to the true solution. And then I use MATLAB to generate a 50 by 50 random matrix A and a 50 by 1 vector B, where all elements are 1. And then we define a K matrix to store the iterated subspace, and then calculate the corresponding Z and X for each iteration. And after 10 iterations, we found that the residual gradually converged, but then increased again. And the MATLAB gave us a warning caused by rank deficiency problem because there was a linear relationship between the rows or columns in the K subspaces. So to solve this problem, we use the Gram-Schmidt process to traverse the basis vectors of the matrix K and perform orthogonalization. And that is to delete the mapping of the new column, which we set right here in the basis vectors of K. So finally, we found that after 10 iterations, the residual gradually converge to 0. So that means this algorithm is correct. So in conclusion, the Krylov's advantage is that it can handle large linear system and has high accuracy, and it can make the value more stable through orthogonalization and it greatly saves computing cost. And however, we have also seen that the problems of this method, we may encounter ill-conditioned matrices or rank deficiency, which may cause a decrease of the accuracy. And the Krylov subspace iteration is an important iterative method in numeric analysis, which is suitable for modern mathematical modeling and industrial application. And there are many optimized versions of it, and which makes the application of this method more extensive and worth learning. Thank you.